Let's learn about Simpson's rule, or what we might call an algorithmic application of the 1-4-1 quadratic approximation. So here's the plan. We're going to recognize how to apply the 1-4-1 rule creatively to approximate signed areas, and then we'll develop Simpson's rule, which is an algorithmic application of the 1-4-1 rule. And once we've done that, we will have obtained a quadratic approximation method for estimating area under the original curve. So we better review the 1-4-1 approximation rule. So remember what the idea is. Given an original graph over an interval, we might be interested in finding the area. And what we could do is by representing sample points equally spaced at the endpoints in the middle, let's call the half width of the interval h, if we could find the function values yl, yc, and yr at the left, right-hand endpoints in the middle, the center respectively, then using all this data, these four quantities, turns out that the area under the quadratic curve that sort of hits those three representative points, that area can be expressed very simply in terms of these quantities as h over 3 times the sum of yl plus 4yc plus yr. And once we know that, hopefully that approximation will give you a decent approximation of the actual area under the curve you started with. So let's take a look at an example of the 1-4-1 rule in action. Suppose we have the function 3 ln of x minus 1, and we're interested in finding the definite integral on the interval 1 to 2. We could apply the 1-4-1 approximation in this case by chopping up the interval into two equal subintervals. The half width in this case is just 1/2, and the function values, the relevant function values, are respectively f of 1, f of 1.5, and f of 2. So if we fit all this data into the template for the 1-4-1 approximation, we would get this expression right here, which we could calculate by hand, so to speak. But if you have access to a calculator where you can store a function into a register, say y1 in this case, then you can use the calculator to crank out this expression for the approximation. So we'll take 1/6 of the sum of f of 1 plus 4 f of 1.5 plus f of 2. And we get about 0.1575. Now you might be thinking, rightly, that if you have access to this device in the first place, why don't you just use its native capability of finding a numerical integral? So we could use, in this case, with the Texas Instrument device, we could just use fn int. We can integrate from 1 to 2 of our original function. And we find out that the numerical integral, according to the calculator, is approximately 0.15888. Now, of these two, one suspects the second one is far more accurate. It's closer to the actual value of the integral. And so an excellent question is, why bother with the 1-4-1 approximation? So we'll return to this issue later. But a bigger point is to notice that the 1-4-1 approximation is certainly legitimate to use to find signed areas. So when the function values are negative, this approximation method still works in the sense that it finds the best quadratic fit to the original curve. Example B here is this sawtooth function that looks very interesting, and it's not at all clear what kind of formula is going to give you something like this. And suppose we're interested in the integral on the interval from 0 to 6. What is that number, or how could we even approximate that number? Well, you might consider using a 1-4-1 approximation, but a moment's thought should reveal that this is a dreadful idea, because the quadratic that fits these three representative points clearly does not represent the graph very well at all over the interval, and the signed area under that quadratic is not going to really match up well with the actual area under the curve. So this isn't any good. What we'll do instead is we will sort of strategically subdivide the interval into pieces that make more sense. So we'll notice this pointy bit at the point 3, 5, and we'll notice an inflection point at the argument 5. So what we could do is we could split up the interval into 3 pieces, each of which is pretty well represented as by a quadratic piece. So there's hope that by applying the 1-4-1 approximation to each of these 3 subintervals, we might get in total a nice approximation. So here we have the 3 pieces on which, each of which, we're going to apply this template. So the value of h is going to be different in each case. In the first interval, subinterval, h is going to be 3/2, and the function values, the relevant function values, are going to be 0, 1.25, and 5. So that calculation can be done on the side, and we get 5 for the approximate area of this piece. Then the next subinterval has half-width 1, and the relevant function values are 5, 3.25, and 2.5. So we can calculate that by itself, and we get a number that's about equal to 6.83. And then the final interval has half-width 1, and function values are going to be 2.5, 2, and 0. And so the final contribution here is about 1.75. Add this all up, and we get about 13.6. So looking at the picture, you can be confident that this is probably a pretty decent approximation because each of the subintervals has been chosen so that the graph looks roughly parabolic. So this is a pretty decent method of approximating this area, which at the beginning, when we first saw it, it wasn't obvious at all how we might approximate the area. So now let's turn to what we call Simpson's rule. What's the setting? You have, say, a gently oscillating function on the interval from a to b, and surely one parabolic curve is not going to approximate the graph very well, but what we might do is we might approximate the whole integral by using repeated applications of the 1-4-1 rule throughout the interval. And indeed, maybe we'll divide up the interval into subdivisions that guarantee uniform half-widths. We'll do this equally, in other words. Now on each subinterval, each pair of subintervals, we can apply the 1-4-1 method. And you'll notice that because the 1-4-1 method is going to require a pair of subintervals, the total number of intervals we use has to be even. In other words, we have to use an even number of subintervals if we're going to apply the 1-4-1 rule repeatedly throughout the larger interval. So let's label the endpoints. We'll start with x0 and label them sequentially. And of course, the last endpoint, if we call it xn, we remember that n must be even for this to work. Now, we'll let the common half-width be called delta x. And now we will apply the 1-4-1 rule on the first pair of subintervals. So we would get this expression, the half-width divided by 3 times the sum of the left-hand function value, 4 times the center function value, and the right-hand function value. So this is our contribution for the first pair of subintervals. The next pair of subintervals would have this expression for its contribution to the area, and then the next pair would have this expression. Now let's just pause for a moment and add these three applications of the 1-4-1 rule together and see what we get. We will factor out the delta x over 3, and then we can concentrate on adding up the other contributions. And you'll notice that there are two expressions that are going to contribute. They're going to contribute to each other. And so in the end, you get this expression. And the thing to notice is the pattern of coefficients. We're getting 1, 4, 2, 4, 2, 4, 1. Which seems to indicate there's a general pattern that's developing. And indeed, if you work out the general case, which we've attempted to picture here, you will notice that there is an alternating pattern of 2s and 4s internally. And at the very end, you have the 1 left over. So it starts 1, 4, alternates between 2 and 4, and then ends 4, 1. And if you move these coefficients into the picture, it becomes pretty obvious where these coefficients come from. So the 4s occur because of the internal 1-4-1 rule. They're always appearing as the center of one of the applications of the 1-4-1 rule. The 2s occur because you're getting contributions at the endpoints of 1-4-1 rules that are adding up together because you're joining these two together. But at the very endpoints of the interval, there's nothing to contribute to those, so those remain 1. So there's the origin of your pattern of coefficients, the very distinctive Simpson's pattern of 1, 4, 2, 4, 2, 4, etc., 2, 4, 1. So this is Simpson's rule, and it's really not worth trying to memorize this formula so much as sort of memorizing the method of applying Simpson's rule. So what's the method really? Apply the distinctive Simpson's coefficient pattern to the sampled function values, and then multiply the sum of all those by delta x over 3. That's Simpson's rule in a nutshell. So let's look at an example. Suppose we have the function 1 over x, and we're considering an approximation of the integral of f from 1 to 7. So we could try to use the 1-for-1 method throughout the whole interval. But if you fit the quadratic to the sample points, you'll see that the fit is just not that great. So let's not try to use a single application of 1-for-1 rule. Let's try 2 applications. We'll take 2 subintervals. And if you fit the quadratic to both of these pieces, well, that's better. But you can see it's still, not all that great. So let's shoot for 3 applications of the 1-for-1 rule. Let's see what happens if we divide the subinterval into 6 pieces. And so we can apply the 1-for-1 rule 3 times. And you can see there's hope here that this fit is going to be quite good. And the common half width will be 1 in this case. And so our integral can be approximated using this rule as the half width over 3 times this expression. And once again, you can see the distinctive Simpson's rule pattern of coefficients, 1, 4, 2, 4, 2, 4, 1. Now, if you were to calculate this, you get about this quantity, 1.958. But the actual integral, just to compare, is going to be ln of 7, or about 1.9459. Now, this is a relative error of less than 1%. So it's a pretty good fit. And you can see in the picture why you might expect that, because just using 6 subdivisions and therefore 3 quadratic pieces, we're able to fit the graph of 1 over x quite nicely on each of those subintervals. And so we would expect there to be a pretty decent fit. So let's think about Simpson's rule in summary. To approximate a definite integral using quadratic pieces, you might choose an even number, n, and that choice corresponds to applying the 1-for-1 rule half that many times. Divide the interval into n subintervals of equal width delta x. Label your endpoints, and then look at this expression. Now, a few comments are in order. The distinctive pattern of coefficients can only fit when n is even. Let's see why. Look at those coefficients. All the 4s and 2s pair up, except for a single 4 that must be left over, and the 1s pair up, which means there are an odd number of coefficients in that pattern. And the only way you can have an odd number of coefficients is if you have an odd number of endpoints. And the only way you can have an odd number of endpoints is if you have an even number of subintervals. So the coefficient pattern is not going to fit unless you have an even number of subdivisions. This expression looks a lot like a Riemann sum, but it's not. But there's good reason for it looking like a Riemann sum. We're going to see later that Simpson's rule with n divisions happens to be equal to the weighted average of a trapezoid rule and a midpoint rule applied with half as many divisions. And because the trapezoid rule itself is an average of left and right hand sums, it turns out that Simpson's rule is equal to 1/6 of the left hand sum using half as many divisions, 1/6 the right hand sum using half as many divisions, and 2/3 of the midpoint sum using half as many divisions. In other words, Simpson's rule is a weighted average of other Riemann sums, and that's why it looks so much like a Riemann sum itself. A few final thoughts. Simpson's rule is simple but relatively powerful. Just with a few calculations, you can get a pretty good approximation of an integral in many cases. However, thanks to recent technology, calculator software, online resources, Simpson's rule's fallen out of favor. Why? Because if you use any kind of technology to calculate one of these Simpson's rule, well, you might as well use that technology to use the numerical integration feature in the first place to approximate the integral and get a better approximation. So there's good reason for it not being taught as often. However, it still might save the day. Sometimes you only have some data points to work with, or maybe just a simple graph. And in cases like that, it can still come in handy if you want to approximate an integral. And finally, don't forget that you can apply the 1-4-1 rules in an ad hoc fashion when the graph's very irregular. Think about example B. You don't have to try to force Simpson's rule onto an example. You can actually choose subintervals of various widths and sort of get a custom fit Simpson's rule for that graph.